everybody, and welcome once again to the next edition of NPTEL online certification course on microelectronics devices to circuits. In our previous module, we have looked into the concept of combinational and sequential logic, and we have also understood that sequential logic is basically a logic where memory is inbuilt into it, and we also saw that unlike combinational, in sequential logic timing is a very important issue. So, we should be able to therefore perceive that at a particular rising edge of the clock, if my data has to be inserted into the system, then how will the sequential logical block react if the data would have inserted much earlier than the rising edge or much later than the rising edge, and what will be the effect on the overall performance of the sequential logic. Keeping in mind, this module is basically, if you look, is termed as clocking strategies for sequential circuit design. So, this is the topic of this module, and the outline of this module is as follows. We will first introduce to you the basic concept of timing, and then we will look into the synchronous design techniques. As we have discussed earlier, there are two types of design. One is asynchronous, right, and we have another is synchronous. What is asynchronous? Well, asynchronous is that when the data is independent of clock, right, external clock, and when data is dependent on clock, we define that to be as the synchronous design. So, for asynchronous design, timing issues are not important, but for synchronous design, timing issues with respect to clocks are very important. In these respects, we look into two major problem areas of clock, and that is one is known as clock skew, another is known as clock jitter, and we will see how these influence the overall frequency of operation of a sequential logical block, and that is what is the fifth point here is all about, that its impact on the overall delay of the system. We will also look into the fact from where skew and jitter do come into picture, because if you know the sources from where it is coming, we should be able to therefore reduce the skew and jitter here, right. So, we look into what is the meaning of skew and jitter, the origin of skew and jitter, and then ways and means of reducing the values of skew and jitter. Then we will have a look at the clock distribution problem, and then advantage of synchronous design as compared to asynchronous design, and then finally we will recapitulate the whole thing. So, this is as far as this module is concerned, and this gives you typically a brief idea about the clocking strategy. Now, let me come to the basic approach, and we will go step by step explaining to you each one of them. So, as I discussed with you, all your sequential circuits, right, have well defined switching events, as I discussed with you, which means that these switching systems ensure that the functionality of the circuit is not compromised. As I discussed with you earlier also, that let us suppose it is a positive edge triggered a latch, or a positive edge triggered a register maybe, which is accepting a data, and then it is giving to a combinational logical block where some computation is being carried out, maybe a logical operation, and after that it is fed into another register where it is storing it for few amount and then giving into the output side. Now, the way the data will travel from input to output through these two registers as well as combinational logical block will determine the speed of the clock, maximum speed of the clock. Now, if for example, I have discussed with you that if the input is much earlier than the setup time of the register, then that data will not be at all inserted into the system and you will get a miss. Similarly, if the data does not hold its value beyond a particular limit after the clock is passed, which is known as T hold, you will not be also able to evaluate the system. So, that is the reason why we define that sequential logical are well defined switching events, based on switching events. Now, so there are two approaches, as I discussed with you in the starting slide. We have got synchronous approach and we have got a asynchronous approach. In this case, as I told to you, all the circuits element will be simultaneously updated with the global clock, which means that there will be a global clock which will be driving all the blocks, digital block within the system, and this global clock, assuming that the global clock is being run in such a manner that the time at which it goes from 0 to 1, rising edge of the clock, is exactly the same in all the blocks, then we will accept that in all the blocks the data will be inserted at the rising edge. I will give you an idea. Let us suppose what we are assuming is, that we will see that this assumption is wrong later on, but for understanding purposes, let us suppose you are driving an off chip clock. So, this is my off chip clock here, right, and it is driving through these interconnects to the various parts of the sequential block here, right, and it goes so these two are almost equal in dimensions. This is the farthest, these two are farthest, and this is somewhere middle which you see. So, somewhere here also I can get. Now, I am assuming that when there is a rising edge of the clock, this event is replicated at this point, this point, this and this, which means that irrespective of the routing interconnect between the clock and the area where you are giving the clock, irrespective of the distance moved, I assume that the clocks always at 0 to 1 transition at t equals to 0, let us suppose, right, and that is a major assumption. We will see that we will break off this major assumption later on. So, that is one important clock, that there will be a global clock, and therefore, the functionality will ensure that by the constraints of the clock generation and proper distribution. As I discussed with you, therefore, the clock going into the system and generating an output logic will depend therefore on the proper synchronization of the clock with respect to individual blocks of the sequential data. This is for the synchronous approach. You can also have an asynchronous approach which is there. The asynchronous approach means that there is no global distribution of the clock. So, there is no clock is required, right. However, so it depends upon what? It depends only upon the rate of flow of data directly coming into the system, right. However, in these cases there is an increased complexity which is with us. The complexity is typically very large, they are complex circuits, right, whereas these are simple circuits where you need to just to route the signal at a particular point. So, this is the basic introduction of a clock. Now, let me therefore define certain definitions or explain to you. A synchronous signal is one that has exactly the same frequency as the local clock and maintains a fixed phase offset with respect to the local clock, which means that if I have a local clock which is coming like this, right, this is a local clock, then if I have a clock which is something like this, sorry. So, it is of the same. So, this is capital T, this is also capital T, say this is width, this is capital T of the main clock, this is also capital T of the main clock, but it suffers from a basic phase difference here. Then we define this to be as a synchronous clock, synchronous signal is synchronous. The signal is said to be synchronized, as I discussed with you. Why synchronized? For example, if you look back into this design here which in front of you, then I have a register here, clock here. I am assuming that the clock transition, these are all edge triggered register, suppose edge triggered resistor. So, whenever my edge goes high, it also goes high, and this register is able to insert one data from the data train here and transfer it to the logical block. So, this is your combinational logical block which does all sorts of computation on logical block and gives you C out, goes to the register 2 and there is output. So, which means that if I assume that the logical block has got 0 delay, then I would expect that the insertion of data at register 1 and the output at register 2 are exactly the same time domain, provided a delay is 0 for the combinational logical block. In reality, not true, and therefore, that gives you a constraint on the total time period of the external clock, right, for a sequential logic. Now, with the clock, as I discussed with you, data can be sampled directly without any uncertainty, and so this is the most straightforward, simplest interconnect design for using your digital technique, synchronous digital technique, right, and it is pretty easy to implement also. There is also another important two types of important designs which is there with us. One is known as mesocronous and another is known as paleochronous. So, I have got two types of design, one is known as mesocronous, right, MESO chronous. In a mesocronous, synchronous we have already discussed. exactly in phase or equal phase and they are same frequency. Mesosynchronous will have same frequency. So, 2 clocks. So, I have a master clock and I have a clock, I have a data train. Then the data train is said to be mesosynchronous provided they have the same frequency, but we cannot say it about their phase. So, phase will be varying, right. In the first case, synchronous case, you will have the same frequency of course, but the phase will be fixed, phase difference will be fixed. So, the phase difference delta phi will be either 0 or some value integral value n, right, and it will remain fixed for all the edges or all the designs, and therefore, this is known as synchronous, right. Whereas, let us suppose delta phi is not equal to 0, right, and it remains like this for a period of time, we define that to be as a mesosynchronous, though your frequency is same. Fine. Paleochronous means basically means that neither this frequency nor the phase is same in both the cases, right. So, there are 3 types of interconnects models available. We will not go into details of that one at this stage, but I will give you a brief idea later on if time permits. So, this is basically a synchronous interconnect methodology which is in front of you, right, and gives you quite a good definition of synchronous timing. Now, let me come to the basic timing analysis. We have already done this in our previous class, but I will still like to give you an insight into once again. So, the first delay which you see is the setup and hold time, very simple. Setup time is defined as the time before the rising edge of the clock when the data should be held stable, so that the input register is able to properly accept the data. What is hold time? Hold time is the minimum time after the rising edge of the clock, same clock, till which the data must be held stable for the clock to understand that a fixed data has come to our system. Now, maximum delay of the combinational logical block is known as TP logic or even T logic, right. T clock 1 and T clock 2 are the positions of the rising edges with respect to clock 1 and clock 2. So, we have done with this, we have done with this, understood setup and hold time. Now, the maximum delay of these registers, this or this, is referred to as TCQ. Now, TCQ CD is defined as the contamination or minimum delay of the resistor. So, TCQ is the maximum delay of the resistor, whereas TCQ CD is basically defined as the minimum delay of the resistor, right. And T logic CD is the combination logical block combination logical block your error in terms of delay, higher delay higher error will be there. So, we have got 5 quantities here TCQ, right, which is your maximum delay of the resistor. TCQ CD is the contamination of the minimum delay of the resistor. So, this is max delay, this is min delay, this is T setup and hold is a clock constraint, right, and then T logic is basically your maximum delay of max delay of combinational logical block, and TIC CD is basically your delay because of the logic itself, right. So, under ideal conditions, as I told to you in our earlier discussion, that T clock 1 will be exactly equals to T clock 2, right, and the worst case propagation determine that the minimum clock period required for the sequential circuit is this much. I think you can understand. See, TCQ plus T logic plus T setup. Why it is like that? Because your minimum clock period of the input clock must take into account the setup time violations or setup time logic. T logic is basically the contamination delay of the combinational logical block, or at this stage the total delay of the combinational logical block, and TCQ is the maximum delay of the resistor, because you see the signal passing through registers through combinational logical blocks and then finally going to the output. So, the minimum capital T, which is the capital T means the clock period, right, this is the clock period, this is the clock period, should be at least greater than T setup, right, because otherwise you will have a problem. T logic also the same thing and TCQ also the same thing. So, capital T should be greater than TCQ plus T logic plus T setup. What is T hold? T hold is that I discussed with you, after the rising edge of the clock, the time till which the data should remain stable is defined as T hold, and it is given as T logic ICCD minus. So, T hold is equals to, so T hold is equals to TCQ CD, which is TCQ CD is the contamination delay of the resistor, the minimum delay of the resistor, plus T logic CD, which is combination delay or the minimum combinational, and you can understand why. So, this logic will have a say 1 millisecond delay, right, and then this is having a 1 millisecond delay, right, and let us also assume that this is having 1 millisecond delay. So, capital T should be at least larger than equal to 3 millisecond. If it is not, then any of the 3 operations will have to be violated, which is not possible in a sequential logic, right. And the worst case propagation delay requires that the delay determines the minimum clock period required for the sequential logic. I will give an example. For example, if you are in a situation where you are using the sequential delay for a very stressed condition, right. What does it mean? That your voltage levels and current levels are very high, then what does it do is that gives you the worst case propagation delay for a sequential logical block, right. So, this gives you the worst case propagation delay in a sequential logical block. As you can see, capital T is greater than TCQ plus TPD logic plus T setup plus T logic, and T hold should be less than TCQ TC bar CD and T logic CD. Now, why T hold should be less than that? Because if it is T hold, let us suppose T hold is greater than that, then what will happen is that either of these two problem areas will be inserted into the logic principle, and there will be an issue as far as output is concerned. So, clock skew, let us look at now clock skew. We have understood the basic idea about the delay concepts. Let us come to clock skew. Because of process variations and environmental variations, the clock signals can have spatial and temporal variations, right. So, how do you define clock skew? The spatial variation in the arrival time of the clock on an IC is referred to as clock skew, which means that I will give an example. Let us say I have a clock here, I have a IC here, and this is driven by two clocks, external clocks. Now, if this clocks take higher time as compared to this for whatever reasons, we define that this clock is basically having a skewed design, right, and you need to formulate it. Why these are required? Because see, until and unless you send all the signals in a transparent mode as well as properly, you will not be able to evaluate the output signal, right, and that is what is happening here. So, what is a clock skew? The spatial variation in the arrival time of a clock transition on an IC is referred to as clock skew. Now, the clock skew between 2 point I and j is given by del ij, where Ti minus Tj, and this is quite important also. So, for example, if you have clock here, right, maybe I can maybe I can discuss here, right, but nonetheless let me see how it works out. Now you see that the spatial variation in time of arrival of the clock transition on an IC is referred to as a clock skew. In the arrival time, please understand, it is not on the terms of delay, or it is not in terms of frequency, it is arrival time which is important. So, if it has arrived later than the clock skew, we will have certain it is known as a positive skew. If it arrives ahead of the rising edge of the clock, we define that to be as the premature case. So, one has to be very careful what is clock skew. As I discussed with you, the clock skew between 2 points in an IC with having I and j as a subscript, we can write del I of j is equal to Ti minus Tj, where Ti is the time taken for the data to reach at that particular point, and Tj is basically the output point with respect to the rising edge. So, Ti and Tj are the position of the rising edge of the clock with respect to a reference. Now, the clock skew can be positive or negative depending upon the routing of direction. So, if the, and I like you to find it out, if the direction of the clock and the data is same, you will get positive skew. If the direction of the clock and the direction of the data movement is opposite to each other, we will get a negative skew, right, and I would like you to find out why and why so. Now, clock skew will remain same from cycle to cycle, right, it does not change. Because it does not depend upon high mismatches and so on and so forth, it only depends upon clock load. But unlike jitter, which we will see later on, clock skew is very stable in terms of the output which is there with me, right, and the clock skew can be, as I discussed with you, positive or negative depending upon the routing and the direction of the positive nature of the clock source. So, let us look at what is known as a positive clock skew. What is a positive clock skew is I have a resistor 1, right, resistor, the combinational logic, and resistor 2 is there with me. Now, I have a T clock 1, T clock 2. So, at the rising edge of T clock 1 nothing is happening, because in clock 2 you already have this thing, you already have a skew, which means that the rising edge will shift by right to accept this data, right, and therefore you get del is equal to this much. Now, in reality it has to also hold the data equals to T h. So, the total delay is basically del plus T h, right, and that is what is seen at this particular point. Fine, is this conceptually clear, right. Now, resistor 2, so resistor 1, resistor, so combinational logical block's job is to accept the data and then do some logical operation on it and then send the data to the resistor number 2. So, till a time this happens, resistor number 2 is sitting ideal, right, and what does combinational logical block try to do? It tries to accept the data from resistor 1 and processes it and give it to resistor 2. Resistor 2 within a few period of time manipulates it and sends it to the output, right. So, the rising edge is delayed by a positive delta at the second resistor. You got the point? Why? Because if you see carefully, by the time this reaches the second register, the clock 1 might have actually gone behind as compared to clock 2 or maybe ahead also, and therefore you can get a rising edge delay in terms of delta in the second register. Okay. As I discussed, if the clock skew is positive, the time available for signal to propagate from R1 R2 increase by delta. I suppose this is clear, no need to explain. For example, if the clock skew is positive, then I get a larger time to integrate my design, right, and therefore it is much easier to do that, and therefore if you look very carefully, a positive clock skew is always beneficial in nature. Now, let us look at the constraint of the total timing delay, right, and the total timing delay is given by T plus delta. Why T plus delta? Because that is the capital T is the total time period when the system is going from 0 to 1 and 1 to 0, and the value of delta, right, can be or value of delta can be found out from this relationship, but the value of delta will not be varying one, it will be fixed one for the fixed cases of interests. So, if the minimum delay of the combinational logical block is small, the inputs to resistor 2 may change before the clock edge of 2, resulting in an incalculation. You got the point? That means if the combinational logical block has very low delay, then the output of gate number 3 exactly matches with the gate number 1 rising pulse, but that has to be available to gate number 2 in order to evaluate that person, right, but it is not available, it is lost. So, that is a problem area of T logic or transistor logic. The constraint of minimum propagation delay through the resistor in the logic would be I will just discuss with you, it is not there, would be this much, right. So, the constraint of minimum propagation delay through what is the minimum propagation delay is the maximum error will be given by this particular formula here, right, and that is what we get from the positive clock skew. Let me come to negative clock skew. Negative clock skew is just the reverse of positive. In the positive clock skew, the data path and the person who is looking at the skew, they were in the same direction. So, if the data path was moving from x to y, the clock was also moving from x to y. Here the reverse is happening. When the clock is moving from left to right, the device is operating from right to left, right, and therefore we define negative is to be negative in nature. The rising edge of the clock 2 happens before the rising edge of clock 1, right, and therefore delta is negative, right, and therefore here delta is kept to be negative. The constant in the minimum time period becomes more stringent, that T plus delta should be greater than or equal to this much. Why this delta? Because this delta is the minimum difference between the setup time and the rising edge of the pulse for the MOS device in the study, and that is the reason it is converted into this simple form where you can understand the T plus delta, which is basically the T plus delta means basically your just a minute, T plus delta basically means your this quantity, right, is always greater than this thing, right, T setup, T CQ and T logic. with this we come to a example scenario of a positive and negative clock skew, right, and you can see here that for a positive clock skew, right, this input coming from R1 is sort of a delay element which goes to R3 directly, right. So, R1 to R3. So, there are 3 registers R1, R2 and R3, and there are 2 combinational logical blocks, combinational logic 1, combinational logic 2. But please understand, to move from R1 to R3 it has to be properly tuned in terms of potentials, so that it can move easily from point A to point B, right. This is the case of positive skew. Positive skew means the data train, which is this one, and the clock, which is this one, they move exactly in the same direction, right, and they move exactly the same direction. Now, so the delay of the combinational logical block is basically your internal delay. Similarly, if the clock is in the opposite direction as compared to data, you will have a negative delay at this point and this point. Now, so during the positive edge of the clock, delta is greater than 0, and therefore I should maintain delta plus t hold should be less than or equals to this quantity, and the circuit does malfunction independent of the clock period. Sometimes there is a malfunctioning in the clock and therefore it stops working. During negative clock skew, when the data is routed to the opposite direction of the clock, we get the negative skew in this case. So, we understood what is a positive skew, what is a negative skew, and it works. Now, timing issue in a data path with feedback. Let us suppose I have a negative skew and this is the feedback which is there with me. I have a logic here, I have a logic which takes care of the logical experts. Then we have got a register in our house. Then this is basically a logic analyzer. Same is the case of this one. These 3 are basically simple players in this game. So, this is basically a positive logic or positive skew, because this is my data train path and this is my movement of the various blocks from left to right, and by using a simple algorithmic problem area, right. Let me come to one more important point, and that is clock jitter, and we will take up this one in a detailed manner in the next turn. Clock jitter refers to temporal variation of the clock period. So, the clock skew was spatial variation, where there is a physical movement of the clock from point A to point B. Temporal variation primarily means that you do have this much amount of variations. So, you initially had 2, at 2 you had this thing, right, and then what happened is after 2, at 2 you are at 1, suppose you are giving a positive edge triggered design here, but what has happened is that you have to wait till this edge number 3 to come, for which you need to wait till this much amount of this thing time domain when the next clock higher edge comes. So, initially it was triggered at 1, it was supposed to be triggered at 1. What has happened is it is not triggered to either at 3 or at 2. So, there will be a small this t jitter which will be there. This is known as a temporal variation. In time domain you will see a shift, and it can vary from one block to another block, right. Jitter almost remains constant from block to block, right, but I am sorry, the skew remains constant from block to block, but the jitter will vary from may vary from one block to another. We will work out the details of it in the later stages, but primarily if you look very carefully in this case, you can see that therefore, clock jitter refers to the temporal variation of the clock period at a given period of time. So, initially you had this into consideration. Now, what has happened is, because of some problem, we will discuss that later on, that it has not shifted from this side to this side, right. Everything has shifted by a particular phase from this side to this side, right. This shifting is there, as you can see the shift is there. So, this was initially here, this shifted here, right, and as you can see therefore, the cycle to cycle refers to time varying deviation of the single clock period. So, you had a single clock period of capital T. Now, because of cycle to cycle variation in the jitter, your new value at location I will be given as T I jitter to be equals to T I n plus 1 minus T I n minus T clock, right, where this is the T I n is basically the clock period for period n, and T I n plus 1 is the for nth plus 1. So, when you vary from first period to the second period, right. So, this is 1, and then as you vary for second period, there is a lateral shifting. So, what has happened is that we define T jitter to be this minus this, the difference, because that is the extra one, minus clock, because why? Because clock is common to both. So, if you subtract that, the difference will come out to you between the various values of skew and jitter, right. So, we will take up the next part of the strategy in the next clocking strategy in the next module. Thank you very much. Hello.
Sir, finished, sir?
This one is finished.
Sir, conclusion, sir, one more time.
And which one? Last one?
Sir, last one, conclusion.
Okay.
Okay.
Shall I start?
Ready, sir? Ready, start.
Okay. So, clock jitter refers to temporary variation of the clock period at a given point of time, which means that the clock can expand or reduce from one cycle to another. So, this is one cycle, let us suppose this is one cycle, right, and I have another cycle. So, this is one cycle, this is another one cycle, and then this is another cycle. So, between this cycle and this cycle, you might have a difference in the rising edge of the clock, which means that this is known as jitter. So, this is a temporal domain, whereas skew is spatial domain. Skew does not change from cycle to cycle, whereas jitter changes from cycle to cycle. We define jitter at any particular point in a given location I to be equals to T I n plus 1, which is basically the clock period for n plus 1th minus T I minus n at nth clock. So, when you go from n plus 1th clock to nth clock, the difference between the two is basically your jitter, but you understand within that you already have the clock period common to both of them. So, if you subtract, when you subtract that, you actually get the overall jitter which is there, right. So, this is basically from cycle to cycle. So, once you have one cycle and you have another cycle, the jitter varies from cycle to cycle, right. With this, we are finished with this first module of your sequential logical clocking strategies. In the next block, we will take care of the combined effect of skew and jitter on the performance of a sequential logical block. Thank you very much.